A warm welcome also from my point of view. During the next roughly 20-25 minutes, Rob and myself will give you a short overview of how in the design of battery cells, costly electrical vehicle recalls can be avoided straight at the beginning by using an additive called succinonitrile, and the succinonitrile that Envalior is supplying is called Stanyl SN. So by using this additive in the electrolyte of lithium-ion batteries, the thermal stability of the cells can be significantly improved, and via this improvement, the risk of the thermal runaway on the one side, but even the capacity retention on the other side can be significantly improved, and as such, the industry can be avoided to end up in sometimes maybe pretty expensive, costly recalls. Now, if you look into electrical vehicles, I'm myself also a driver of an EV. The range of the vehicle is always of a big concern, both for the consumer or end consumer as the driver of the vehicle, as well as, of course, for the OEM. And in order to achieve a high driving range, the industry has been focusing basically to find the right balance also with the weight of the car, to optimize the cells in the perspective of very high capacity and very high energy density, so that the amount of cells can be basically limited to not overdo it with the weight, while at the same time still squeezing out as much range as possible. Now, if you look into lithium-ion batteries, they are basically built up of three components. It's a cathode, it's an anode, it's an electrolyte in between, where then the ions and the charging and discharging are moving from one side to the other side. Now, the industry, in order to improve for capacity and for energy density, on the cathode side has been largely looking into nickel-rich or manganese-rich or cobalt-rich ternary alloys, so that the capacity and the energy density can be pushed to a max. On the anode side, silicon-based or tin-based carbon composites have been prime focus. We will focus primarily in the cathode and show you a way how in the build-up of the cells, the cathode can be protected so that potential corrosion of the cathode or potential harmful gas generations inside the cell can be minimized. So main focus will be on the cathode side from our perspective. Now, while this kind of ternary metal alloys for the cathode are delivering actually a very good job in terms of capacity and high energy density, there is also one downside. And the downside is that it's not very helpful in terms of thermal stability. The thermal stability of this kind of nickel-rich or cobalt-rich or manganese-rich cathodes is actually pretty low. And because it is low, it results into a high risk for thermal runaway. And this thermal runaway, once it gets out of control, it can lead to fires. And this fires is basically what is sometimes picked up by the media and goes then viral over the internet, and people all the way down to consumer level get very afraid of that one. So very good from a design perspective, but with one downside. And that one downside will be the focus of today's discussion, how to reduce that one. How to make it very clear, because there's, of course, always very intense discussions about how different platforms are comparing. There is very strong and reliable data in the industry which clearly show that the amount of such fires in an electrical vehicle is significantly lower compared to a combustion car or compared to a hybrid car, which is good because then at least we know what the baseline is. Yeah? There's data from companies like Tesla or from PINFA or also auto insurance, which prove that what the real statistics about such fires in the real life are. So we talk about significantly less, but, and that makes it a bit critical, despite being less, since the root cause of such fires in an EV compared to a combustion car is different. In a combustion car, fires are basically very often related to leaks on the fuel side. And then if you have somewhere an electrical spark or a crash, that can very quickly lead to a fire. So it's logically very clear and traceable from the root cause perspective. In the case of an EV, such fires can be generated by battery shorts or all the way down to manufacturing issues like contamination in the cell. It's a bit more unreliable. And statistics shows that such fires can be generated during the charging, during driving, in a crash, can even happen if there's water ingress inside the battery, or what is basically the most critical point is that the car can even be parked without any charging, and still, as a consequence of the cell and the thermal runaway inside the cell, the end result can be a catastrophic fire from that perspective. So it's fires, while statistically much lower compared to ICE or compared to hybrid cars, but because it's so unpredictable, it's psychologically basically pretty risky, because nobody really knows what can happen. And worst case, imagine you have a house where your garage is even integrated in the ground level of your house, and you park your car inside the garage, and then you go to sleep in the sleeping room, which is maybe even one level higher than your garage, and suddenly overnight you get a fire. So that gives a little bit of psychological insecurity for the consumer in that case. At the same time, there are also quite a couple of very costly recalls already happened in the industry from different manufacturers, and what is worse, even people died in such kind of fires. So it's not something which we talk about from a pure theoretical manner. It is happening despite having a lower statistical impact, but it is pretty highly visible and extremely costly, all the way to people who get killed. From that point of view, also no surprise that regulation is increasing focus on avoiding this kind of fires, or it is reducing the impact on the life of people. In 2021, China was globally the first country which started with such regulations that they imposed on the industry. They introduced a 5-minute time between the onset of thermal runaway and the moment when fire or smoke is basically exiting the battery pack. And of course, it's all about risk mitigation, gives the consumer enough time to basically escape that critical area. Last year, India, as another big important territory, started to follow. They also implemented this 5-minute escape time. And the whole intention is, no matter whether you are driving a 2-wheeler, 3-wheeler, or a 4-wheeler, to give the driver enough time to basically safely park somewhere the car at the side of the street, and then bring himself to a safe situation. So that's about avoiding the impact on life, basically. Since most of the lithium-ion batteries in the future, specifically those with high weight and high capacity, will be used in the mobility segment, so in electric vehicles, it's also clear that the biggest focus of regulation in the industry in terms of improving safety will be put on the mobility space, so for electrical vehicles in the upcoming future. Now, if we talk about fires and thermal runaway, we have to basically keep in mind that there are two sides. One is avoiding the propagation of a fire. So that's basically what regulation is now mainly focusing on. Once the onset of thermal runaway has started, how do you ensure that there is sufficient escape time so that the life of people is not threatened? And that is all handling with avoiding or at least delaying the propagation of a thermal runaway. The other side of the coin is, how can the industry step up in the design of batteries or cells or packs so that the thermal runaway can be avoided straight away at the beginning? Now, if you look into thermal runaway, there are a couple of reasons or root causes why thermal runaway can be generated. There can be contamination during the cell manufacturing, so very tiny particles where the cell manufacturing is not overly clean can already be enough to generate local stress, and with that lead to breakages of the cell insulation and can lead to a thermal runaway. It can be shorts in the design of the battery, can be a physical damage, stone or whatever can damage the battery. Can also be bad treatment of the battery. If the battery is not regularly going into maintenance, and you know that every OEM has regular maintenance intervals for electrical vehicles, or if the consumer is overcharging the battery or the electronic circuitry, the control system is not properly working and it ends up in overcharging, or if the temperature control of the battery is not well done and the battery gets overheated. All of these reasons can lead to thermal runaway. Same as, of course, also the inner cell chemistry, where the cathode can start to degrade. And in that degradation process of the cathode or electrolyte, also harmful gases can be generated. Then it can start the onset of thermal runaway, and in the worst case, can even lead to an explosion of the cell. Now, Envalior is active actually on all three areas. We are supporting our customers to implement a proper thermal management so that the environmental surrounding from a temperature perspective is controlled nicely and precisely, in avoiding to go too low, but also avoiding to go too high in temperature. We are very active in confining and delaying the fire propagation with various structural designs, from individual components all the way to complete battery enclosures in an injection molded polyamide solution. Today, we will only zoom into how can the cell chemistry of a lithium-ion battery be modified so that the onset of the thermal runaway can be avoided. Yeah? So while we are active in the entire ecosystem, we will zoom in today only into that one focus point, how to improve the cell chemistry, and based on that, how to increase thermal stability. And because thermal stability of the cell is improved, the risk of thermal runaway is reduced. Now, if you look into lithium-ion batteries, for every designer, there are basically three key focus areas: having a high safety, having a good reliability, and having also basically as high energy density as possible. Now, cathode materials like LCO or NMC are basically the prime materials to achieve pretty high energy density. And specifically for lithium-ion batteries, we recommend the use of succinonitrile or Stanyl Succinonitrile from Envalior as an additive to the electrolyte to stabilize the thermal performance. It can also be used for LFP type of batteries, but the real biggest impact you will get the higher your energy density of the cells get. Now, if you look into lithium-ion batteries from a market perspective or from a demand perspective, there are market reports which predict that the mobility segment, specifically the light vehicles, will pick up the majority of the demand. So while originally it started in the consumer electronics with portable electronics, now electrical vehicles have already been taken it over clearly, and in the future the ratio will be even much more pronounced towards electrical vehicle as the main end market for such lithium-ion batteries. And within this kind of lithium-ion batteries, nickel-based metal cathodes are basically taking the majority of the share, so that the capacity and also the energy density can be really as high as possible. Now, Asia is already very strongly leading in battery design and battery manufacturing. However, North America and also Europe are recently catching up pretty nicely. A lot of new gigafactories have been announced or are already in planning or in the construction phase. And for this American and European gigafactories, it's of course even more important to also have a reliable supply, not only of the battery cells in itself. That's why they are localizing it in also outside of Asia to be close to the end markets. Specifically also for all kind of additives which are used. Yeah, so ideally also these additives are supplied locally, and that's where the additional added value of Envalior comes. We are not only globally one of the largest succinonitrile suppliers to the industry, but at the same time we have a European manufacturing supply chain, so that we can give a good and short supply to these upcoming future markets for lithium-ion batteries. Now, to give you a little bit of a feeling what really happens inside the cell, at the bottom here of the slide, you see a schematics of a cell. Yeah? On the left side, the anode, on the right side, the cathode. And take a look primarily into this green layer. Yeah? In between the white area is the electrolyte. So these are the three components of the battery cell. At the top, it's a standard battery cell, and at the bottom, it's already a cell with the impact of succinonitrile. And what you see is the succinonitrile is forming this kind of protective layer on top of the cathode. And because it forms the protective layer on top of the cathode, it avoids that the cathode can get basically corroded. And because of that, the cycling capacity is improved, and also the generation of harmful gases is significantly reduced. At the same time, succinonitrile also helps to avoid the dissolution of metal ions from the cathode, and it helps to stabilize the decomposition of the electrolyte and to protect the electrolyte from oxidation. So that's basically the key effect of the succinonitrile. A very thin, roughly nanometer thick layer is deposited on top of the cathode and acts as a protective layer, and with that safeguards the decomposition and the corrosion process on the one side, but also avoids that harmful gases are generated, and the capacity of the cell can also be extended. And with that, I hand over to Rob. Rob can now zoom in a bit in more detail in explaining you what happens exactly on a chemical process and how to basically understand the real impact of succinonitrile on the cell performance.
Good. Well, Tamim, thanks very much. I would like to, in the remainder of this presentation, zoom in on 3 points. First one is to elucidate a little bit better on what we know about how succinonitrile works as a safety-enhancing battery additive. Secondly, discuss a bit more precisely what benefits succinonitrile brings to the battery performance. And thirdly, to discuss how succinonitrile compares to alternative nitriles that you can also buy in the market. Now, what do we know about how succinonitrile works as a safety-enhancing battery additive? Basically, what has been figured out by, let's say, people at universities, but we have internal confirmations of that too, is that at a high enough voltage, succinonitrile reacts with your cathode, so it does not adsorb onto the cathode, but really reacts with your cathode. So it gets oxidized preferentially before the carbonate electrolytes get oxidized, and then forms a thin protective layer on the active cathode particles that basically protect the electrolyte from oxidizing further. So basically, if you look at the slide on the left-hand side, reaction 1 that involves succinonitrile runs at lower voltages, at lower cathode potential, you could say, than reaction 2 that involves carbonates. And the consequence of that is that you get a thin protective layer on your carbonate, on your active particles that protects reaction, prevents reaction between carbonate and active particles. This has been proven well, and let's say the net consequence of that is essentially depicted in the picture on the right. The black line is for an electrolyte, carbonate-based electrolyte that does not contain succinonitrile. And what you see is if you raise the voltage of your cathode high enough, then at some point there is an oxidation current, which comes from basically oxidation of your carbonate, so they start to react. And if there is nitrile, a small dose of nitriles in your electrolyte, then that reaction is absent, and you can basically protect your battery better against higher voltages. So basically your electrolyte becomes more suitable for operation at higher voltages. You can also see this protective layer on the active cathode particles. For instance, this is most easily seen if you look at the two SEM photographs on the right. The top one is for active particle that was basically present in an electrolyte that did not contain succinonitrile. The bottom one was present in an electrolyte that did contain a little bit of succinonitrile. And what you can see is that there's a thin nanometer thick layer on the active particle. Here it's 2.3 nanometers that has this, let's say, voltage protective action, preventing carbonates to react with high voltage cathodes. So it leads to a voltage stability of your electrolyte. Now, it is very important to also address this point. What we have also found out internally is that succinonitrile may also react, if you don't take precautions, with the anode side of your battery. And that has consequences, negative consequences for the internal resistance of your battery. So this is unwanted. You see that in the picture on the left. So here we made lithium symmetric stacks, succinonitrile in between. And if you store these at high enough temperatures and you monitor the resistance of your stack, then you see a runaway of the resistance of your stack. This is unwanted, and what we have found is that you can prevent these things by using succinonitrile in combination with second additives that basically form a protective layer on the anode. So then you can, and that is basically shown in the picture on the right. You see that the voltage, the resistance of your stack is now constant and low. So the main message is succinonitrile, very good to enhance the voltage and the thermal stability of your battery, but you have to take care of what happens on anode side, and therefore you always have to use it in combination with second additives such as fluorinated ethylene carbonate, but there is other additives that can do the same. Vinylene carbonates, VEC, vinyl ethylene carbonate, and there is more of those. So if you want to have more information there, feel free to contact us. Now, then about the second topic, what specific benefits does succinonitrile bring to your battery? This is best seen by looking at the first line and the last line in this table. So look at line REF1 and X1. Basically, this is an NMC graphite cell, and it has the top line has a standard electrolyte, so combination of EC, EMC, DMC, and let's say at the bottom line we have added succinonitrile to get that cathode protective action, but also second additives to get the protection on the anode side. And yeah, what you see is that the benefits of that, let's say, cell that contains the extra additives is that it has a better cycling stability, so less capacity reduction with after 300 cycles in this particular case. But it also, if you store the battery at elevated temperatures, in this particular case 60 degrees for 1 month in this charged state, that is the last column, then you see that the battery that contained succinonitrile additive was much better able to retain its original open circuit voltage, which was 2.4 volts. It was charged to 4.2 volts. So the voltage of it is much more stable. If you don't use this additive, then you see that because of reactions between electrolyte and cathode, there's basically a voltage reduction occurring. So it is basically temperature stability and voltage stability that you're getting when you're using this additive, succinonitrile, in combination with other additive that protects anode. Now here you see a second very much related benefit. This was a basically lithium cobalt oxide graphite cell that we built in a pouch bag, a big cell, 1200 milliamp hour. So this cell was charged to 4.35 volts, stored for 1 week at 60 degrees Celsius. And then after that, we cycled it a couple of times at room temperature. And what you see is that the cell, the blank that only contains, let's say, non-doped electrolyte, simple carbonates only, has a much higher, basically thickness evolution. So the pouch bag blows up to a much larger extent. So there's much more gas evolution than for the pouch bag that contains the succinonitriles. So basically, you can say that succinonitrile protects the cathode, leads to suppressed electrolyte degradation, gas evolution, and thermal energy release as a consequence. And what is very important and not shown by us internally, but you can find this in open literature, it is included on the slide. It has been shown that this is also the case for batteries that are exposed to even higher temperatures, such as 130, 150, where your separator may already melt. In those cases, because of the protective layer on the cathode, also there is much less gas evolution and thermal energy evolution if such an event occurs. So this is really protective action of your nitriles that you're getting. Okay, then very briefly, the last topic: how does succinonitrile compare to alternative nitriles? A very well-known one is a diponitrile, which is basically a larger molecule, has more CH2 groups connecting the nitrile groups. Well, what we have seen is that if you look at the cycling at room temperature, there's not too much difference, at least for the first 100 cycles. But if you go to higher temperatures where you blow up the speed of the chemistry, so if you cycle the battery at 60 degrees C, then you see that succinonitrile outperforms a diponitrile and also some other succinonitriles that are made in a different process and that are probably less pure than the nitrile that we produce via a continuous process. So so far from the data that we have, we see that our product, small molecule with a lot of nitrile density, has the best protective action. And then the final slide on comparison to alternative nitriles. It's also very clear from these pictures that we have not generated ourselves, but you can find in open literature. Nitriles have very little effect on the conductivity of your electrolyte, the sigma, and on the viscosity of your electrolytes. And in fact, succinonitrile, which is the red dot, has even the least effect on the conductivity and the viscosity. So there's no viscosity increases and no conductivity losses. Okay. This now brings me to the conclusions. I think by now nitriles are very well proven to protect the electrolytes in lithium-ion batteries. It is particularly applicable in high energy density lithium-ion batteries where you charge to somewhat higher voltages. Works in lithium cobalt oxide batteries, has proven to work in NMC type batteries. I think from the data that we have available, you can say that it outperforms alternative nitriles as well as competitors succinonitrile made in a different process, batch versus continuum process. We have shown that it works because it forms a thin reactive layer, on the cathode particles, protecting, basically blocking to some extent the interaction of carbonates with active cathode particles. And then finally, and I want to stress this again, a very important point, if you think about using this additive, do realize that you have to use it in combination with second additives such as FVC, VEC, VC that also protect the anode. And this is basically what I wanted to tell.